Okay, today we're going to do a short little section of notes on a free body diagram. And a free body diagram is just a simple diagram in physics that we use to show all the forces acting on an object and in whatever direction they happen to do. So this first example, let's suppose we were to hold the book up in the air. So we're going to hold it up in the air and not move it so it'd be stationary. So if it's up in the air, what we do is we draw our diagram so that we have the box, and you can just use a box or circle, something simple to show the book. So in this case we got the book, and we draw our diagram from the center of that object, and we have gravity pulling it downwards, so the force of gravity is pulling it straight down, and then we would show the other force acting on it, so me holding the book up in the air, so I'm pushing upwards in the air, and we call that our applied force, or FA. So a few different forces that we have acting on things. So force of gravity typically is always acting on objects. So force of gravity. And we'll calculate that later on. We're going to look to see how to calculate that. And then we'd have FA is typically the applied force. That's somebody pushing on something or lifting it up or something along those lines. So those kind of are our two main ones. And the key idea is if whichever force is bigger, that's the way it's going to go. So if I'm holding a book up and I don't match the force of gravity, then it's going to fall down, right? It's going to be stronger gravity, it's going to go downwards. If I push up on the book harder than gravity or stronger than gravity, then it's going to actually move upwards. Okay? So pretty simple concept, just the idea of balancing forces and so on. So let's do another object. So let's say in this case we have a book again, but instead of being held up in the air, this time it's going to be sitting on top of a desk or a floor or something like that. So in this case we still have gravity going downwards, but now I'm not applying a force to hold it up. Instead, the force of the floor, it's strong enough to withstand the force of gravity. So instead, this case, we call it a normal force. So we say Fn, which is the normal force, and the normal is just sort of the opposite of the gravity. So in this case, gravity's pulling it downwards, the floor is pushing an upwards force against the book. So that's what we call the normal. And a key thing to remember is the normal force, it's always perpendicular to the surface. Okay, so in this case, our normal force, it is at a 90-degree angle to the ground, so that would be good. So if, for instance, let's suppose we had, let me just redraw it here. So let's suppose we had the book again, but it's on a ramp. Let me draw a triangle. Okay, so let's suppose in this case, though, we've got the book, it's on a ramp, and we've got our object, it's sitting on the ramp. Okay, so in this case, gravity is still downwards. Gravity is always going to pull it straight down. But in this case now, our normal force, it's always perpendicular to the surface. So our normal force is going to be upwards like that. It's not going to be opposite to gravity. So because those two things aren't balanced, the book should end up sliding down the ramp because those two forces are not balanced, and gravity is going to, the downwards or the horizontal part of the gravity is going to win out on that battle. Okay, a few other kind of forces that we have. So we've talked about those basic ones. So let's suppose we got a box on the floor, we got gravity pulling it down, we got the normal force, so this is on the floor, so we got normal force acting upwards. Let's suppose we're going to push it to the right, so we're going to have an applied force to the right. Then in this case, there's going to be some sort of resistance or a force that's going to pull it backwards, so we call that one the force due to friction. Okay, so the friction, it could be the friction between the surfaces, it could be wind resistance, it could be anything like that. So any kind of resistant force, we'll call it the force due to friction. And the key thing with friction is it always goes in the opposite direction of motion. Okay, so in this case, we're moving the box to the right, so our friction has to go to the left. If we go back to our ramp question, it's also friction, so let's suppose it's going to go downwards, it's going to slide down the ramp. In this case, then our friction would be opposite. It's going to be pointing upwards of the ramp. Okay, so it gives you kind of idea how friction works. And the last one that we're going to look at is if we had the tension. So tension would be sort of the same idea as an applied force. The only thing that would be different is if we're pulling. So we're pulling an object with a rope or hanging something from a rope or something like that. So let's suppose we have a sign or something like that. We're going to tie it to a rope and let it hang down. So we'd call that the force of tension. And then in this case, we got gravity still going downwards. So tension is sort of like an applied force. They sort of mean the exact same thing. The only thing that's different is whether you're pushing or pulling, and like you're using a rope. So the tension in a rope is typically how the question would be worded. So it'll ask for what is the force of tension, which would be the same kind of thing as an applied force. Okay, I think that takes care of everything. So just kind of be careful of labeling them. And then the other kind of force that we use often is net force. And that's what we're going to talk about in our next lesson. So the net force, we don't really label it on the diagram, but just like the word sounds, it is our net force. So it's basically what is the resultant force, or another way of thinking about it is the sum of all the vector forces. Okay, so that's where we're going to end today, and we'll look at the net forces in the next topic.